In this video, we are exploring how to determine if a function is continuous at a particular point. And in general, continuity, the easiest way to think about it is frequently said that if you can draw a graph or a portion of the graph without lifting your pencil or making a really jerky, like pointy bit, if it's a smooth curve, and you don't have to lift your pencil or pen off the paper, then generally speaking, that graph or that portion of the graph is said to be continuous. But this is the formal definition of continuity. So a function f is continuous at a point x equals c if f of c is defined, so it actually has to be defined at that point. It cannot be undefined at that point. That would make the graph not continuous there. Also, the limit as x approaches that point, c, of the function has to exist. If the limit does not exist, the function would not be continuous at that point. And then also the limit as x approaches c of the function has to actually equal the value of the function if you were to substitute c into it. Okay, so those are the three requirements for a function to be continuous. If a function is not continuous at a point, the term that we use to describe it is that it is discontinuous there. So at any given point on a graph, a function can either be continuous at that point or discontinuous at that point. And here are a few examples of what this could look like. So in this first graph here, this one, number 1, we can see that we have a function that has kind of a smooth curve here, if I read it from left to right up until it hits this point x1. And then it has an open circle here and here, right vertically above x1. And then it continues off in a smooth curve to the right. So the smooth curve parts are no problem, right? Informally, we can see that this graph is not continuous at x1 because we would have to lift our pencil when we're drawing it, right? So it's not continuous there. Specifically, it's not continuous here because we've got actually a couple of problems. If we go back to our definition, f of c, if we're treating x1 as the point c, it has to be defined. Well, it's not actually defined at that point. The function ceases to exist there because these are both open circles. Also, the limit at that point does not exist, and it's not equal to the value of the function if we were to plug x1 into the function. We, as a matter of fact, can't plug x1 into the function because the function is not defined there. So this particular function, our first function, is discontinuous at x1. If we look at our second function here, we can see we have a horizontal line, again, reading the graph from left to right, horizontal line that goes all the way up to this x value at x2, where it has a closed circle. Then we jump up to another horizontal line that proceeds to the right above the x2, but it's got an open circle at the x2. Now, by contrast to the first graph, this function does actually exist at x2, right? It is defined at x2. It's defined at whatever this particular point happens to be, the closed circle, okay? So it's not that it doesn't exist there. However, if we start looking at things like the limit existing, right? The limit as x approaches c of f of x exists. The limit doesn't exist here because if we look at it coming from the left-hand side, whoops, there we go. Coming from the left-hand side, we would get one value. Coming at x2 from the right-hand side, we would get a different value. So the limit here does not exist. Therefore, this graph is discontinuous at x2. Whoops. Let's fix that. X2, discontinuous. Okay. Then when we're looking at this third graph over here, we have a nice smooth curve. Here there's a hole in the graph in the middle of our smooth curve, and there's a dot above it. So again, we can see that this informally is discontinuous, because to draw the entire graph of the function, I would have to pick up my pencil or my pen. When we're thinking about these criteria, okay, is f of, in this case, x3, is it defined? Well, yeah, it's defined at this point up here, whatever that value happens to be, it is defined at that point. Does the limit of f of x exist at that point? And is that limit equal to plugging in that value to the function? Well, no, right? Here's our function value at x3, but that's not the same as what the limit would be. Okay, so this one is also discontinuous at x3. And so that is the idea with thinking about when functions are continuous at a point or discontinuous at a point. A lot of functions that we deal with routinely, like for example, if we're thinking about quadratic functions, or if we're thinking about cubic functions, or if we're thinking about, what else? Just linear functions, right? Like a straight line. All of those are continuous everywhere. There are no jumps in the graph. There are no breaks in the graph. There are no holes in the graph. So a lot of the functions that we're used to dealing with, these kind of regular, everyday, well-behaved functions, they're going to be continuous. You really have to worry about discontinuity when you're dealing with kind of some of the more, I guess, exotic functions, if you want to call them that. Piecewise defined functions, functions that have holes, functions that have asymptotes, right? Those are the functions that we have to worry about whether or not they are continuous.